What if the universe was never supposed to exist? And the fact that you are sitting here right now, breathing, thinking, watching this, is the result of a cosmic accident so improbable that scientists have spent decades trying to figure out how it happened, and still don't have a complete answer. Because here is the thing. According to our best, most tested, most precise theories of physics, the ones that have been verified in laboratories to an accuracy of 1 part in a trillion, you should not exist. This planet should not exist. The sun should not exist. Galaxies, stars, atoms, chemistry, life, none of it should be here. The universe, by every right, should be a vast, cold, perfectly uniform ocean of pure energy and absolutely nothing else. No matter, no structure, no complexity, nothing. The fact that there is something instead of nothing is not just a philosophical puzzle. It is the deepest unsolved problem in all of science. And the answer, whatever it turns out to be, will change everything we think we know about the nature of reality. Let's start at the beginning. The very beginning. 13.8 billion years ago, in an event we call the Big Bang, the universe came into existence from a state of almost incomprehensible density and temperature. In the first fractions of a second, fractions so small they don't have everyday names, the universe was a seething, expanding fireball of pure energy. And then, as it cooled, something happened. Energy began converting into matter. This is not magic. This is physics. Einstein's most famous equation, E equals mc squared, tells us that energy and matter are equivalent. They are 2 forms of the same thing, and under the right conditions they convert into each other. And when energy converts into matter, it does not produce matter alone. It produces matter and antimatter in perfectly equal amounts. Every time. Without exception. This is not a theory. This is something we observe happening right now in particle accelerators all over the world. You cannot create a particle of matter without simultaneously creating its antimatter twin. The universe does not allow any other outcome. So in those first moments after the Big Bang, as energy crystallized into particles, it should have produced exactly equal amounts of matter and antimatter. An electron for every positron, a proton for every antiproton, a neutron for every antineutron. Perfect symmetry, perfect balance. And here is what happens when matter meets antimatter. They annihilate each other. Completely. Instantly. A particle and its antiparticle collide, and both are converted back into pure energy. A burst of photons of light. Nothing remains. No matter. No structure. No atoms. Just light. So if the Big Bang produced equal amounts of matter and antimatter, which it absolutely should have, then everything that was created should have found its twin and annihilated. Every particle of matter meeting every particle of antimatter, converting back to energy in a flash of pure light, until nothing remained but a universe of photons slowly spreading apart in the dark. A universe of light. Perfectly symmetric. Perfectly dead. No atoms. No chemistry. No stars. No you. And yet here we are. The universe is overwhelmingly made of matter. Everywhere we look, every star, every planet, every gas cloud, every galaxy matter. Not antimatter. We have searched. We have looked at cosmic rays, particles raining down on Earth from across the universe, and they are matter. We have observed gamma-ray signatures that would indicate matter-antimatter annihilation happening on large scales in space, and we see some of it at the center of our galaxy, small traces, but nothing like the wholesale annihilation that should have happened everywhere at the dawn of time. The universe chose matter, or something caused matter to win, and we don't know why. This is called the baryon asymmetry problem. Baryons are the particles that make up ordinary matter, protons and neutrons. And the asymmetry is the fact that there are vastly more baryons than antibaryons in the observable universe. The ratio is staggering. For every billion antiparticles that existed in the early universe, there were approximately 1,000,000,001 particles of matter. One extra particle for every billion pairs. That tiny, almost undetectable imbalance, 1 part in a billion, is the reason everything exists. 1 in a billion. That leftover residue, that rounding error in the cosmic ledger, after all the annihilation was done, was enough to form every atom in every star and every galaxy in the observable universe. Your entire body, every atom in it, is made from that 1 in a billion survivor. You are the leftover. You are the remainder. You are what the universe couldn't destroy. Now the question is why? Why was there 1 extra matter particle for every billion pairs? Why wasn't it perfectly even? Something in the laws of physics must have broken the symmetry between matter and antimatter in those first moments. Something must have treated matter differently than antimatter, even slightly, enough to tip the balance. In 1967, a Soviet physicist named Andrei Sakharov, the same man who helped build the Soviet hydrogen bomb and later became a Nobel Peace Prize-winning dissident, sat down and worked out the conditions that would be necessary for matter to dominate over antimatter in the early universe. He came up with 3 requirements, now called the Sakharov conditions, and they are among the most important statements in all of cosmology. The first condition is that there must be processes that violate baryon number, meaning processes that can create more matter than antimatter or destroy antimatter without destroying an equal amount of matter. The second condition is that these processes must also violate something called CP symmetry, the combination of charge conjugation symmetry, which says physics should look the same if you swap particles for antiparticles, and parity symmetry, which says physics should look the same in a mirror. If CP symmetry holds perfectly, matter and antimatter behave identically, and you can never get an imbalance. The third condition is that these symmetry-violating processes must happen out of thermal equilibrium, meaning the universe must be expanding and cooling fast enough that the reverse reactions can't undo the imbalance as quickly as it's created. The Big Bang satisfies the third condition easily. The universe was expanding at an extraordinary rate in its first moments. The first condition, baryon number violation, is predicted by certain extensions of the standard model of physics and by grand unified theories, though we haven't directly observed it yet. The second condition, CP violation, is the crucial one. And here is where things get genuinely exciting. We have found CP violation. It exists. It has been measured in particle physics experiments. Certain particles called kaons and mesons behave slightly differently from their antimatter counterparts. The symmetry between matter and antimatter is not perfect. The universe does treat them differently. Physics has a bias. Not a large one, but a real one. And that bias is the reason you exist. The problem is the amount of CP violation we've observed is not nearly enough. Not even close. The CP violation measured in kaons and mesons is orders of magnitude too small to explain the 1 in a billion excess of matter that we observe in the universe. Something else, some additional source of CP violation, some deeper asymmetry in the laws of nature, must have operated in the early universe. And we haven't found it yet. This is the heart of the problem. We know the answer must involve CP violation. We've seen CP violation. But the CP violation we've seen is like finding one drop of the ocean when you need the entire Pacific. There must be more. There must be a source of symmetry breaking that we haven't discovered yet, operating through physics we don't yet understand. And finding it is one of the central goals of modern particle physics. One of the most promising places to look is in the behavior of neutrinos, those ghostly, almost massless particles that pass through matter almost entirely without interacting. Billions of neutrinos pass through your body every second. Right now. From the sun, from cosmic rays, from nuclear reactions in the earth. You cannot feel them. You cannot stop them. A light year of lead would only stop about half of them. They are the most antisocial particles in the universe. And yet they might be the key to why you exist. Neutrinos come in 3 types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And they do something deeply strange. They oscillate. They change flavor as they travel. An electron neutrino produced in the sun can arrive at Earth as a muon neutrino. The identity of the particle literally changes in transit. This was confirmed definitively in the late 1990s and early 2000s, and the physicists who proved it won the Nobel Prize in 2015. Neutrino oscillation is only possible if neutrinos have mass, something the original standard model of particle physics said they didn't have. So the standard model had to be extended. The universe surprised us. Now here's the critical part. If neutrinos can oscillate between flavors, and if that oscillation violates CP symmetry, meaning neutrinos and antineutrinos oscillate differently, then in the early universe, neutrinos could have played a role in generating the matter-antimatter asymmetry. This is called leptogenesis. The idea is that in the very early universe, certain extremely heavy neutrino-like particles, called right-handed neutrinos, predicted by some extensions of the standard model, decayed in a CP-violating way, producing a slight excess of leptons, particles like electrons and neutrinos, over antileptons. This lepton asymmetry was then converted into a baryon asymmetry, through a process called Sphaleron transitions that occur at extremely high temperatures. The math works in principle. The scale of the asymmetry that leptogenesis can generate is in the right ballpark. It is currently one of the most compelling explanations for why the universe is made of matter. But it's not confirmed. We can't directly test the original heavy neutrinos because they would have existed only in the first tiny fractions of a second after the Big Bang at energies we cannot reproduce. What we can test is whether ordinary neutrinos show CP violation in their oscillations. And this is exactly what several major experiments around the world right now are trying to measure. The T2K experiment in Japan, which fires a beam of neutrinos 295 kilometers from a particle accelerator to a detector, published results in 2020 suggesting that neutrinos and antineutrinos do oscillate differently, a hint of the CP violation that might explain our existence. The result was not yet definitive, but it pointed in the right direction. Larger experiments, Dune in the United States, Hyper-K in Japan, are being built right now specifically to nail this down with higher precision. We may have an answer within the next decade. But let's take a step back even further, because there's something even more unsettling underneath all of this. We keep asking why matter won over antimatter, but we haven't asked a deeper question. Why does antimatter exist at all? Why does the universe have this symmetry, even an imperfect one, between matter and antimatter? Why is every particle matched with an antiparticle of equal mass and opposite charge? The answer comes from one of the most beautiful theorems in all of mathematics. In 1940, Wolfgang Pauli proved the CPT theorem, which states that any relativistic quantum field theory, any theory that combines quantum mechanics with special relativity, must be invariant under the combined operations of charge conjugation, parity reversal, and time reversal together. You can break any one of them individually, or even two together, but all three together cannot be broken. The existence of antimatter is not an assumption or a choice made when building our theories. It is a mathematical necessity. It falls out automatically from the combination of quantum mechanics and special relativity. In a universe that obeys these two frameworks, antimatter cannot not exist. The universe has no choice. And this leads to something that physicists find deeply beautiful and deeply terrifying at the same time. The CPT theorem means that for every way matter behaves, antimatter behaves in a way that is the mirror image in three dimensions simultaneously: charge, spatial orientation, and time. Antimatter is, in a very precise mathematical sense, matter moving backward in time. This is not poetry. This is what the equations say. Richard Feynman, one of the greatest physicists who ever lived, pointed out that a positron, the antimatter counterpart of an electron, is mathematically indistinguishable from an electron moving backward through time. The Feynman diagrams that physicists use to calculate particle interactions treat them identically. Whether this means antimatter literally travels backward in time in some physical sense, or whether it is simply a mathematical equivalence, is something physicists still debate. But the fact that the question is even coherent, that the mathematics permits it, says something profound about the nature of time and reality. Now let's ask the question everyone is thinking. Where's all the antimatter? If the Big Bang produced close to equal amounts of matter and antimatter, even with the 1 in a billion imbalance, then after all the annihilation was done, there should still be some antimatter left. There was one extra matter particle for every billion pairs. But a billion pairs means a billion antiparticles. Where did they go? They annihilated. Every last one of them. In the first second of the universe's existence, the entire primordial stock of antimatter, billions upon billions of antiparticles for every single matter particle that would go on to form the visible universe, found its matter partner and annihilated in a burst of light. The photons from that annihilation are still with us. We can detect them. They form part of what's called the cosmic microwave background, the faint glow of heat that permeates the entire universe, the afterglow of the Big Bang, and in it are encoded the photons produced by that cataclysmic matter-antimatter war fought in the universe's first second. Every photon in the cosmic microwave background is a memorial to an antiparticle that existed and was destroyed. The universe is filled with the ghosts of antimatter. And here's the number that puts this into perspective. For every atom in the observable universe, every atom in every star in every galaxy, there are about 2 billion photons in the cosmic microwave background. 2 billion photons for every atom. That is the ratio of the annihilation product to the survivor. For every one of you, every atom that makes up your body, there were 2 billion antiparticle annihilation events. You are 1 in 2 billion. Your existence required the destruction of 2 billion antimatter particles for every atom in your body. The universe paid an unimaginable price for you to be here. Now we need to talk about something that makes this entire problem even stranger. When physicists make antimatter in particle accelerators, and we do every day in facilities all over the world, it behaves exactly as the equations predict. Antiprotons have the same mass as protons. Positrons have the same mass as electrons. Antimatter atoms, which we have actually created for very brief moments at CERN, appear to have the same spectral lines as regular atoms, the same responses to light, the same internal structure. Matter and antimatter, when we study them in isolation, appear completely identical except for their charge. We have not yet found, in any laboratory experiment, an asymmetry large enough to explain the cosmic imbalance. The matter-antimatter asymmetry of the universe is encoded in some property or interaction that our current experiments have not yet been sensitive enough to detect. It is hiding from us, deliberately, if the universe can be said to be deliberate, keeping the secret of its own existence. There are physicists who believe the answer lies beyond the standard model entirely. Supersymmetry, the idea that every particle has a partner particle with different spin, predicts new sources of CP violation that could be large enough to explain the asymmetry. But the Large Hadron Collider at CERN, which began colliding particles at record energies in 2008 and has been running experiments ever since, has found no evidence of supersymmetric particles. They should have shown up by now if supersymmetry is real at the energies we've probed. Their absence has been disappointing to a large part of the theoretical physics community, though it doesn't rule supersymmetry out entirely. The partner particles might simply be heavier than we expected. Others look toward extra dimensions. String theory predicts that space-time has more than the 4 dimensions we experience, 3 of space and 1 of time, and that additional compact dimensions exist, curled up at scales too small for our experiments to detect. In theories with extra dimensions, the apparent weakness of gravity compared to other forces, a mystery called the hierarchy problem, finds a natural explanation, and new sources of CP violation can arise from the geometry of the extra-dimensional space. These ideas are mathematically rich and theoretically appealing. Whether they correspond to reality is something we cannot yet say. And then there is the possibility that the answer is even stranger than any of these. Some physicists have proposed that the matter-antimatter asymmetry might not have been generated by any specific interaction in the early universe, but might instead be explained by the anthropic principle, the observation that the universe's parameters must be compatible with the existence of observers, otherwise there would be no observers to notice. On this view, there may be a vast number of universes, a multiverse, each with slightly different physical laws and constants. Most of those universes ended up with perfect matter-antimatter symmetry and are empty and dead. We happen to live in one of the rare universes where the symmetry was broken enough for matter to dominate. We couldn't find ourselves in a dead universe, so naturally we find ourselves in a live one. This argument makes many physicists deeply uncomfortable. It feels like giving up. It feels like saying the universe is the way it is because if it weren't we wouldn't be here to ask. That's true, but it's not an explanation. It doesn't predict anything new. It doesn't point toward any experiment we could do to test it. Most physicists want a real dynamical answer, a specific mechanism that broke the symmetry, not just an observer selection argument. But the possibility that the anthropic principle plays some role cannot be entirely dismissed. Here is what we know for certain. The universe exists. Matter dominates over antimatter by a ratio that cannot be explained by the CP violation we've measured so far. The Sakharov conditions tell us what must have happened, but not how. Neutrinos might be the key, and experiments right now are trying to find out. The answer is somewhere in the physics we haven't fully written yet, in the territory beyond the standard model, in the particles or interactions or dimensions we haven't discovered. And when we find it, we will have answered not just a question in particle physics. We will have answered the question of why there is something rather than nothing. We will understand the mechanism by which the universe chose to exist. Think about what that means. Every civilization that has ever existed on this planet, every philosopher who sat awake at night wondering why there is a universe at all, every religious tradition that proposed a creator to explain the presence of existence, every poet who felt the vertigo of realizing they were somehow here against all odds, all of them were circling the same question without the tools to answer it. And right now, in underground laboratories and mountaintop detectors and particle accelerators that took billions of dollars and thousands of lives of work to build, human beings are closing in on the answer. We are one generation, possibly two, away from knowing why matter won. From knowing why the universe kept one particle in a billion instead of annihilating everything. From knowing why you are here. You are a collection of survivors. Every atom in your body outlasted a billion antimatter twins. The fact that you are breathing right now, the fact that you can feel wonder at this, is the endpoint of the most improbable cosmic lottery ever held. You didn't just win the lottery of being born. Your atoms won the lottery of being allowed to exist at all. And somewhere in a laboratory, right now, a physicist is running a calculation or checking a detector readout that might, just might, be the first clear signal of why. That is the most astonishing sentence that has ever been true. If this cracks something open in you, if you feel that particular kind of beautiful vertigo that only the deepest science can produce, share this video. Someone in your life needs to feel this today. And subscribe, because this is what we do here. Every single time. Now I need to hear from you. Does it comfort you or terrify you that you exist because of a 1 in a billion cosmic accident? Drop your answer in the comments. I promise I will read them.